my first idea was to speak about this fight between wave function people and density functional people, and how heroic it was, and how we finally won it. But then I said, well, maybe there is something else. Think about the future. What still remains as a problem? What were the arguments people had? And so my first point is, well, there was someone who opposed DFT even after it became a fashion. That was Kucernik. And Trygve reminded at lunchtime about his after dinner talk, and he even wrote it, distributed it before it was published, and then he published a long article about it and a second article. And said, maybe I should look again what his argument is. Kucernik has to be taken seriously if he has something to say. And he has 11 claims about DFT, and he marks them, well, I have to get used to this. I admire this technique. With this WK, Werner Kucernik in blue, what he says. And I think there are some existing issues in DFT. I would like to speak about it. But in all these fights, there was also a human factor. I think that this is was also something which was important. So the scientific opposition is not fully justifying what happened and what remains to be done. And for this, I try to speak to someone from social sciences. And so finally I found a review paper, which is quoted here. And the paper is about something else, but there are a lot of points, and in social sciences they see things in a much more detailed way than I'm seeing. And the idea is how to make decisions when uncertainty is present. That is a point. Uncertainty is present, and we always have to make, well, how do I know if my function will work or not? So, important warnings. This is my viewpoint. I don't claim it's not really a scientific talk. So, well, it's how I feel. So we can argue about it after my talk, during my talk, during dinner. So first about mathematical foundation. So there were some of Kucernik's points. The partition of the density functional, the approximations we are making, and at the end I will speak about this human factor. And not all points, there are many points. So he said, Holmberg-Kohn was 64, but until Lee published the papers in the 80s, it was mathematically wrong. And and I think this is still true with TD-DFT mathematically. If I talk to a mathematician, he will not say TD-DFT is mathematically clean. So, okay, what comes now? What we know about wave function theory, Schrödinger and Heisenberg were in 25. The behavior, mathematical treatment of the behavior as a wave function at coalescence is, well, you see a paper of they published a series of the papers in the year, around the year, in the year 2000. And there are still papers coming out about representing 1 over R in plane wave basis, how to treat this. So there are still issues. So I think my personal viewpoint on this, that there are mathematicians who work hard in electronic structure theory, and they are interested in doing it. So you mentioned Mathieu Levin, for example, also, and I'm very optimistic about this side. And maybe I don't care so much about the mathematics. It should be right for my level. So there are some issues that are not so important for me. Well, the question is Holmberg. There is a question which I think still remains. This is in this density functional theory, the connection between density and there are many potentials that give nearly the same density. So Evert Jan had 20 years ago, 25 years ago, 30 years ago, something showing or Gaussian basis set, you take a Gaussian basis set, generates a constant potential. Here you can see, here, you see for the you change the potential, and the density is changed. That's the density response function. You decompose it in the way you decompose natural orbitals. You have like natural orbital occupation numbers. You have some numbers, and you plot them in decreasing order. So the numerical values for the hydrogen atom, this response function is known analytically for the hydrogen atom, are these dots. And you use Slater or Gaussian basis functions, so they get bad for high oscillation, 30. But what you see is the decay is very slow. I don't know mathematically what's the decay law of this, but you have many, many components. Well, we say, of course, they have more and more nodes, there are oscillations, but they build up, and you can have many potentials that give you similar densities. And this is one hypothesis. Then he says that introduce the term zoo of density functional. Is it an explanation for the zoo of density functionals? Because, well, you can have many potentials and get nearly the same thing. So it's just the opposite of the Holmberg-Kohn theorem. Okay. Werner Kuzelnik says the kinetic energy in density functional theory has no meaning. Does the expansion in Slater, in terms of Slater determinants, have a physical meaning? Antisymmetry is respect, but physical meaning, okay. So I think arguing about physical meanings is a very vague concept for me. Now comes another point, the partition of the density functional. You have the universal density functional, but we partition it. So already the Holmberg and Kohn put in the paper, they had a partition of the universal density functional. How do I? Here. So inverse into a functional g of rho, and a known part, which is the Hartree part, that it's clear that something like that is needed. The nuclear repulsion is treated exactly. The nuclear electron repulsion is treated exactly. It's separated. What do we do with a classical electrostatic interaction? Well, you have to take it out, because otherwise we have a very strong imbalance. Then, where is the de Pauli principle in this f of rho, or even in this g of rho? Where is it? Well, you put it into kinetic energy. That's where it's most important. There's a Conchat method. So, yes. Well, and then you can say, well, what do you do? Maybe you should separate exchange and correlation. You take a smaller part. Surer has worked on this, Stoll worked on this. So it's about older paper. I was very proud. I thought I was the first doing a self-consistent calculation of this, and met Vosko, and he was very, very kind. Then he mentioned, you know, I published it in 1977. They showed me a paper before I did anything in a journal of nuclear magnetic resonance, something like that. So this was an idea that was around, and I still think it's interesting. And then you can say, what is transferable? And this is an idea I like, that the short range is transferable. When electrons get close, the effect don't depend on the external potential. And we know that's physical, and it should be this way. And Peter has just mentioned this range separation, which uses this kind of idea. And so we have hybrids and double hybrids, and so on. So, well, so we have this partition, we partition, repartition, repartition. And that, do you know about Mullah Nasreddin? I probably don't know. I don't, one, okay. Or Nasreddin Hoja. And this is a statue from Bukhara. And he's very well known, and there is a story. So he digs a hole in his garden. And the neighbor looks over the fence and says, what are you doing? Well, I'm digging a hole. And what do you do with the earth from the hole? Well, what a question. Make another hole and put it in there. And what do you do with the next this earth? Well, look, I'm working. I have no time for discussions. Well, Well, that is the analogy to this. Okay, now we come to the difficult part, the approximation. And he says, DFT is not serious because it only gives a frame. Nobody tells us how to do the approximation, because there's something also I don't like with people. The universal function is unfortunately unknown. It's very well known. Even mathematicians blessed us with saying, well, Sleep or Mel Lewis, you search over all wave functions with give a density, and you can do it numerically. We did it numerically, things like that. So you can do it, but it's very expensive. You don't want to do it. You want approximation. And then he says the variational principle, and I mean, he uses, what he means is that the approximation energy is not larger or equal to the exact energy. That's what I think what he means. You don't have, the exact energy is not an exact. He doesn't say it explicitly, does not hold for density factor approximation. Well, it's true. Wave function theory gives a frame, from my viewpoint, and it does not hold for the gold standard of CCSD parenthesis T. So my view on it is true. So how important is it? And I have now only two questions. What do you do with machine learning? So should we reject machine learning with this argument? I don't think so. Is this not? And for energy difference, is a variational for that 2.1 and 2.2. What do we do about energy differences? Does it help us? I don't think this is. So, okay. Next. This is the point which was raised by Witao and often so formulated differently by Fortean about the localities that is used in approximation. And this is this self-interaction error problem. And what is a local approximation for the heart rate energy? And Peter just mentions it's a problem that you want to approximate this term, and this turns very strongly from one system to another. And of course, as for the hydrogen atom, it's relevant for the exchange because you don't approximate it, but you have just one electron. The exchange has exactly to compensate this heart return that you don't want to approximate. So, and this is this. I think there is another error with Neil degeneracy, and that's a very old paper. And what is here? They are the errors we obtained in dissociation energy, and it was, at this time, the benchmarks were just these diatomic molecules. And you see here LDA, self-interaction corrected GGAs, and they go all wrong here for this correlation functions. But if you add the static correlation, it works much better. And when it was clear that the static correlation, and when that takes this static correlation, there was a paper by Lai Clementi, where Clementi came with this idea that static correlation should be treated by, he said, a different treatment related to this beryllium series and this kind of. So, and the crosses are also GGAs of 86. So I think this is near degeneracy was a problem in DFT and still is a problem. So it has self-interaction error. It's just one aspect related to degeneracy because it also, there are, so this plane wave. So another criticism was a systematic improvement. So say DFT semi-empirical, there is no systematic improvement. And there is a question of the attitude to parametrization. Should what just discuss the last minute. And you can say even LDA exists through transfer from calculation from a system to another system. So it exploits a universality argument. Say a density function is universal, but of course it's not universal because you make LDA. The LDA is not universal. So, wave function theory, of course, claims systematic improvement. So I don't know when is the complete basis set limit reached, when is the full CI limit reached. Can we discuss this way? So I have now, to present my viewpoint, I put a citation from Walter Kohn. I don't remember his exact phrasing, but essentially what he said was speaking about some method. He said, without comparison to experimental results, they would not know if their results were right or wrong. And I think this is also valid for, in general, in quantum chemistry, unfortunately, because we don't compute bounds, because that's what a mathematician, Werner Hackbusch, once told me. He said, why do you call your methods approximations? Approximation has something to do with proximity. In mathematics, proximity is defined by bounds. Do you give bounds? Call them, how should we call it? Call them models, but not approximations. So, well, by this kind of argument, of course, again, an argument against machine. So I come now to the next point about the other point, the human factor. And there are different aspects in this which are related to, well, the need of exploration, the way we take decisions, and the way we communicate. Exploration. There is something, well, I've heard something. Now you find a lot of things on internet, and if you don't read the books, you can listen to a talk or someone who defines hedgehog and foxes, and he calls hedgehogs those who relate everything to a central vision, and foxes who entertain ideas that are rather centrifugal than centripetal. They go in different directions. And this is something I liked in the DFT community. When I came to the DFT community, there were many different viewpoints. And they were exchanged in a very constructive attitude. People could differ in the opinions, but it was never aggressive. So when I started, that was, say, my main reason to stay in DFT, was not because I had the approval of the quantum chemistry community, but because there were the people I met there were so kind and so open to ideas. And this is something that I find a criticism to as an empiricism in density functional theory, because when this was introduced, the idea was to have an immediate success. And just put away this openness and thinking, think, oh no, just take our time, let's see how things happen. Now I come to a more difficult question, and this is, I think that this is a point that interests me most now. And it is what makes density functional approximation work. And people would say the Holmberg-Kohn theorem, and the Holmberg-Kohn theorem is beautiful, I admire it. It's just this formulation of Liebert. You look at this and you ask yourself, how was it possible it took so much from Schrödinger to get to this? But is there something else behind it? Is something else in density functional approximation? That's one. And there is an alternative interpretation. And this was mentioned by Bob Jones this morning, when he said, he was mentioning, this was his 74th paper, and he mentions a paper by Lengress and Perdue, and the paper by Gunnarsson and Lundquist. And I don't know, maybe this 77th paper was also mentioned today from Effortian. And well, the idea is you switch from the Kohn-Sham system to the physical system, switch to Hamiltonian, and see what happens, what the exchange correlation function comes out as a correction during this process. And this viewpoint, which appeared already in the first talks, having this whole viewpoint, was very important, not only in understanding density function, but also in constructing density function. And I think John would agree that it was, for the GGA, it was the leading idea, and I think it is there. And I will present something with range separation here. So you have a model Hamiltonian, mu stands for model. You have the kinetic energy operator, the external potential, and you have some long-range interaction. Why is a long-range interaction? Because what I want to correct is a short range, because this is universal. Should not depend on the potential. And then by this parameter lambda switches from one to the other. And this V is a bare potential. It's no adjustment to a mean field potential, no Conchamp potential, nothing. So you see that this ansatz is a bit, there is something, it's not what people really want. It's what I want, but not what people really want. Because there is still this interaction here. And you don't want. You want this parameter mu to be 0 to have no interaction. But I have an idea about what short range means, and so I take away the long range. Unfortunately, we are still allowed to study what we want to study. And now you combine just the technique. The basic of this technique was something which Paula developed 2006, where she said, well, let us look for this kind of potential interact model. What is the behavior of the wave function short range, and how does it go over to the physical interaction, to Kato-Kask condition? And these are some numerical result. I have more, but I show you just one. This is work in progress, but what you see here is the energy as a function of this parameter. So the model is this is what the model is giving. This when you look here, the model is giving this. So, but no, sorry, I don't even show you the model. Sorry, it's not the graph I wanted to put. The model is has an error of half a Hartree. For the non-interacting, this is a bare potential, is half a Hartree. It doesn't enter this picture. If I take just a wave function, I have the expectation value, I get this red dashed line. But you see here, there is a whole regime where the errors are very small. So I enhance this region. And you see that this region where the background is whitish, that's a region of chemical accuracy. And you see that you correct just knowing this behavior. What happens when electrons come together? You have practically no error until the moment arrives when things break down. And I have some ideas how to get further, but there is the method now, it's a present. How it is now, it's just as like it. There are a whole series of methods where things go well and then they break down. When you say, oh, I want really to arrive to Conchamp, I don't know what to do. What's the universality I should apply? I know about Kato-Kask condition, but I don't know what to apply when there is no interaction. So there is no transfer for any system. I just use the behavior. There is no empirical parameter. There is no fitting to anything. So, can do it. The results were with a bare potential. You can try to, you look at the density you get. The density is very bad. So you can see here that the curves are what you have seen before. The densities are this. You improve the densities, and you get the difference between full and dashed curves. So in this regime, where we work in the universal regime, it doesn't even matter if you use a mean field potential or the bare potential. So, of course, if you go to weaker interaction, this will matter. This will matter a lot. But otherwise, in this universal regime, it does not. So that was my point. Is it, maybe there is something different behind density functional approximations. Now let me come to the way we decide. So how do we decide about something? And there is, I don't know, probably several of you have read this book by Kahneman with slow versus fast thinking. And, you know? Well, he says he's a psychologist who got a Nobel Prize in economy. Oh. Yes, something like that. They made tests on people, and the point is that, his point is that from the time when the tiger was jumping on you, you were not have time to think, to calculate its trajectory, to just run away. And so we have a tendency to make this decision by fast thinking, but if you just sit down and think a little bit, you see that your decision was the wrong one. And the other, this would be an evasive solution. And there is another factor, we trust experience. So if I have a wave experience with wave functions, I don't know, it was maybe what Peter was saying before about Popper. She had the experience with wave function, he didn't trust density function, but you don't have your own experience with, you don't know, you have to try it first. So with you have your experience with wave functions, see how things progress, why should you go over to DFT? And the idea that we trust things and expect it will continue this way is typical for machine learning. And there is, the point is that this produces a kind of inertia, so people repeat past choices regardless of new evidence that comes in. And for me, this is a good explanation for the difficult acceptance of density functional approximation. And the question is, so how do we judge the quality of density functional approximations? And so here the question was benchmark. So we had G1 and G2. So it was mentioned before. And there was, at the same time, there was Ansel, who made the D-Gauss, who had published systematically many compared with NP2, and he had full of tables of results. And so the moment benchmarking came in, I think this was an important point for making density functional accept, to get out of it. Well, choosing the relevant benchmark is not a trivial question. At least I see it so. And statistical summaries may be misleading. I don't want to say much about this point, but I take an example. We tried for machine learning, and there were people who tried, we took the data, they fit it on coupled cluster, and they got MP2 quality. And we looked at how they fit it, and thought, no, look at the distribution of errors. It's not a Gaussian distribution. You have missed something. You have to have something like an active learning you mentioned this morning. If you do something like that, you correct your data. And okay, they did it, and the coupled cluster results have coupled cluster quality. So now the question is the influence of the group in which you are. If you are once in a group, you let yourself influenced by the group. And there is this was something which is also known as a majority rule. It's Condorcet from the French time of the French Revolution, that democracy is good. So he shows mathematically that if you have several jurors, each taking a decision with a probability larger than 1/2 for educated people, equally, the majority vote is better than the individual knowledge. So it's a mathematical problem. And there are also more recent things about this. But one condition is that the probability should be larger than 1/2, otherwise it's worse. So and group members may converge too strongly. And this is something which is, there were in the 17th century, there was there were a tulip mania, so where they were speculated with tulip bulbs. And there were fortunes made within hours, and then everything crashed. And I don't know, this is sick with these sudden changes. That how makes, I think this majority rule might have had an influence on acceptance or rejectors of DFT. And now, how objective are we in our choices? And there is, we see, well, there is a question that if we do together something, things are better. So all pull on the same rope. And this goes funding things that are fashionable. But is it really good for science? Well, I don't know. And another point is the status or the reputation of the people. Someone, if Popel says something, or Kohn says something for chemistry or physics, well, it's little discussion about that. Another point is about what Kucelnik says, there are false statements. I think they are rather unclear statements. So he says the density is not a derivative of the energy with respect to the potential. It's a one-to-one correspondence between density and potential. The density gives the potential gives, sorry, that's a mistake, it gives the Hamiltonian, that's everything. We speak about the universal density functional, but it's just a density functional. Why do we use the word universal? Kohn-Sham is not a density, but a reduced density matrix method. So, do we need more clarity in our formulations? And I have now another joke. I don't know. So a man goes to the psychologist, says he has problem with his wife. And he realizes that the man is a bit nervous. And he says, okay, well, look, you know something? I tell you something I do. You walk 10 kilometers every day, and you call me after 1 month, with the hope he will calm him down. And after 1 month, he gets a phone call. So, oh, yes, I'm calling you as promised, and how do you feel? Well, perfect, everything is fine. And with your wife, perfect, now that she's 300 kilometers away. You think it's a joke, but you recall, so John can tell you the dispute he had about Kryachko, because not using the term antisymmetric for the constraint search. Sometimes it's a question. So I arrived to the conclusion. I have here, I took from Google Scholar the citation of density functional, without citation, without pattern, so in thousands. And you see, it went up, it went up, and then strongly down. So what's going on? Does it have a future? Well, this year it went up, and I think it's a source for many ideas. Thank you.
Thank you. Any thoughts and questions? Anybody want to comment here?
May I start? You seem to be able to take us out of the box a bit, so I'm going to ask you a question that may seem to the whole audience to be a bit out of the box. You mentioned that Kucelnik had actually suggested that the kinetic energy operator and the orbitals that we get from them and so on are physically meaningless.
Yes, yes.
But the interesting thing to me, I'd say call it a paradox, is why don't we ever question that kinetic energy term? You know, if you ask that question, you may think that since we can't touch it, nobody touches it, it may be very physically meaningful. So meaningful that we somehow feel that we can't do without it, and there's no bother, nothing to bother about.
Well, I think in order to react to this, I would have to ask you more what you mean by what you said.
No, but you know, why is it? I mean, the Hulmer-Cohn theorem says we don't need such a Hartree-Fock term in the density functional, and that has been supported by Mel-Levy and so on. But you know, after the Cohn-Sham proposal, nobody has questioned why we absolutely need that kinetic energy term in the form of a Hartree-Fock.
It's because we need the Pauli principle. That's my answer is because we need the Pauli principle. You have the same density for non-interacting particles that are bosonic or fermionic. And how do this? You look at the density, and now you have to recognize. It's also related to the question with the constraint search, saying the constraint search constrains the wave function to give you a constraint antisymmetric wave function.
And that's the only way?
Well, no. How can you recognize the antisymmetry? Because that's what we are interested in. If you are interested in bosonic system, well, that's another story.
I'd like to disagree with one of the points you made.
It's good.
So, in terms of approximations, you can pretty much rigorously show that the local density approximation for exchange is the universal limit of all electronic systems.
No, I agree. Even I would, not only the universal limit, there was also the, when Mel showed that if you make such an ansatz, it's just a scaling property. I know what you mean.
Well, it's only true when you scale to that semi-classical limit that I'm always talking about, that Lieb-Simon proved for the total energy.
Yes.
But it is universal. Every electronic system, when you scale to that limit,
of course,
it'll become relatively exact.
Yes.
And that is the underlying basis for why.
Is it also exact for correlation?
Correlation is higher order in that limit, and that is why essentially chemists use different correlation functionals than physicists.
But anyway, just you see, so I think we agree on both statements.
Yeah. So I mean, just to comment on that, I mean, the local density approximation, it's not an approximation because it's exact for the homogeneous electron gas, right? By definition.
No,
but
this is quite independent of the idea of the uniform gas. This is true for every inhomogeneous system. So it's a universal limit of inhomogeneous systems, which you can easily calculate by looking at a uniform gas. But we've heard a few statements this morning about this and why, you can't buy a cylinder of gellium. It isn't a reference system, it's a universal limit of all electronic systems.
Yeah, but it's a limit, so what's the bump?
The relative error goes to zero in that limit.
Discussing words here. So, do we need a Hulmer-Cohn theorem?
It's beautiful. No, I think if something is beautiful, you just maybe I told you that I thought about staying one more night in Stockholm to catch a concert. He's a good pianist. I thought about that. It's just if it's beautiful, we need it. Absolutely need it.
One last comment then.
Let's comment on your comment. We do need Hulmer-Cohn to make Cohn-Sham a DFT. Otherwise, it will be a density metric functional theory. Because Hulmer-Cohn for interacting and for non-interacting both are true. So it is completely determined by density.
But you can set up CDFT and there's no Holm-Bacon theorem in it.
That's a different story.
That doesn't depend on that.
But for consent to call it DFT, you need Holm-Bacon.
Okay, I'll think about that. So that we can have a break.